Hello, very good evening to all of you. So today we'll be starting regarding the Fourier transform. So let's get started with the Fourier transform. So when I talk about the Fourier transform, what does it mean is that it is the frequency domain analysis of any of the signals. So as far as the Fourier transform is concerned, so in case of this Fourier transform, it's a mathematical tool. Primarily, I'll write Fourier transform as a mathematical tool, and it's used for frequency domain analysis. Frequency domain analysis. It's used for frequency domain analysis. And if a function like the Fourier transform of x of t is given as x of j omega, or in some books you will find it straight away as x of omega or x of f. So which signals will be having Fourier transform? That is of prime importance to us. So the signals that would be having Fourier transform, that is very important. So we will be seeing that Fourier transform will only exist for a signal, which is Fourier transform exists for a signal for a signal which is absolutely integrable. That means after you do the integration of the signal, you get some finite value. Okay, so that means if you are doing a Fourier transform, so if you have to represent a Fourier transform of a function x of t, so there are two formulas for it. One is the integration from minus infinity to plus infinity. This is minus infinity to x of t, and you'll multiply it with e power minus j omega t dt. So you have this any of the signals. Suppose you have a signal like this, wherein you have a function that is your unit step function u of t. So you can see the value of t from 0 to infinity is 1, but whereas from minus infinity to 0 it is 0. The function is having 0 value. So the Fourier transform will be only, it is only possible, Fourier transform of a signal is only and only possible if the signal is absolutely integrable. That is one of the thing, and this is possible for Fourier transform you will get for power signals, and you will get for energy signals, and the signals and some impulse signals and impulse. Okay, but the thing is that the impulse signal is neither energy nor power. So you don't have Fourier transform for neither energy nor power signals. But this is an exception which you will be studying in the later case. I'll be showing you how does this work out. So this is how does the Fourier transform look like. So this is the and inverse of Fourier transform. If you have to write x of t, that would be equal to 1 by 2 pi minus infinity to infinity x j omega into e power j omega t d omega. So this is the inverse Fourier transform. One more important conclusion is that the frequency of this is given in hertz, that is cycles per second, whereas the frequency here is given in radians per second. Okay, so now let's go to analyze how this Fourier transform work and how what is the use of the Fourier transform. Let's see some standard exponential signals, and then we will go to the properties of the Fourier transform. Let's move and see some three signals which are the standard signals, and let's see how the Fourier transform of these signals, and we will be studying. Suppose you have a signal uh, x of t, okay, is equal to e minus a of t ut, where a is greater than 0. I am asking you to calculate the Fourier transform. As I told you, it can be given by x omega, or it can be also given as x of j omega. So as you see this function, yeah, let's stop here. So to in order to get this function, let me redraw that. So we know the unit step function over here. The unit step function was up to here it is 1, after it is 0, from minus infinity to plus infinity it is 1, and up till here it is 0. Now if I have to write the Fourier transform, I'll straight away write omega x omega would be equal to minus infinity to plus infinity x of t into e minus j omega t dt. What is my function? X of t here is this, so I'll substitute here in that function minus infinity to infinity e power minus at u of t into e power minus j omega t dt. So this minus infinity to infinity can be broken down into minus infinity to 0, e of minus a of t, u of t, e minus j omega t dt, plus 0 to infinity, e minus a t, u of t, e minus j omega t dt. Now you can see from minus infinity to 0, the function u of t is equal to 0. Since this function is 0, here this value becomes 0, so whole signal becomes 0. Now we are only left with the signal 0 to infinity. Now we can take out common value here, and u of t value here in this 0 to infinity, the value of u of t is 1, so we can substitute this value as 1. Now you can take outside, see this is minus, so you can directly write e minus a plus j omega t, okay, and integration. So integration of it would be equal to integration of e power minus 2x is how much? E power minus 2x divided by minus 2. So here also same, this is e power minus a plus j omega divided by, let's take this minus sign here, a plus j omega, and here inside we have to apply the limits, that is 0 and infinity. So this minus signal goes here, so we are left with minus 1 by a plus j omega, and this becomes infinity, this whole signal e power infinity, okay, minus e power 0. So this becomes invalidated, and this becomes minus 1. So minus 1 into minus 1 a plus j omega, so this signal you are left with 1 by a plus j omega. So this is nothing but the Fourier transform of the signal e minus at ut, where a is greater than 0. Now let's see for the signal what would be the response for the signal, wherein we have, yeah, let me go down, yeah, okay. Now let's see for a signal that is, you have one more, you have a signal that is e power at, let's take a signal e power at, and u of minus t. So now the same thing, same expression, x of omega would be equal to, Fourier transform of the signal would be equal to minus infinity to infinity. Instead of x of t, you have e power at, u of minus t, and dt minus t, e power again minus j omega t and dt. So u of t was made like this. U of t was like, sorry, where are the pens here? I'm sorry. Okay, so yeah, what happened to the pen? Okay, in the next this thing class, I'll be explaining you about the other signals, and let me end this meeting here. Okay, so if you put in the similar way and you draw the conjugate symmetry, you'll understand. I'm ending this meeting. Okay.